There we go. Copy. Oh, hey. There we go. Done. Close. All right, here we go. Hey, what's up, man? Good to see you again. How was your weekend? Hmm. Oh, she's running a little slow today. Let's see. See, upload speed. Oh man, it's a little choppy. It's gonna be a little choppy today. So hopefully it's not too bad. So, mm, yeah, it was a good weekend. It was very nice outside. Uh, got me thinking about Hey Morgan, how are you? Got me thinking about fishing already this summer. Got my license renewed the other day, so we will get going with the plans for the summer. So because it is rapidly approaching us, isn't it? So here we are. It is the 29th. If you guys can't see that, probably because my face is in the way, but oh, was it, man? Yeah, what's going on? So, is school keeping you busy? Work or what? And yeah, we have one, two, 3 weeks until spring break. So the 5th, the 12th, we'll meet online for those two, and then we have these three right here for the Zoom calls, and then yeah. What is going on? My internet is not happy today. It was absolutely fine this morning. What's the deal? So, hang on just a second. Yeah, there should be no problem with that. Well, regardless, we're still recording, so even if this is crappy quality right here, we will upload it a little bit later. Painting office in new place. Nice. Oh yeah. So moving always puts a little bit more stress on the weekly activities. When I moved into this house, my current house, I did so over the process of about 5 months, to tell you the truth, because we did a lot of remodeling, and it was just way easier to get that done before we even moved a single thing into the house, even though it just took a while. I was really busy at the time, and so I would come over here, work on it on Saturdays, and then go to work for the entire week. And I did not try and do any extra work on Sundays. So at that time, it was like, no, you still need to get um, your downtime in, because otherwise those projects, they just eat up everything. So that's cool. I'm glad you found a new place, man. So painting your office, yeah. Oh yeah, I should probably do some painting someday. Not no no, I'm not gonna do that. Maybe next year. So yeah, especially with school and work and all kinds of stuff going on. But that's okay. So it'll feel good once you get all settled in. So it'll feel real good. I always used every chance that I moved, and I haven't done this in a couple of years. Well, I think it's been about 7 years now since we moved into this house. But when I sold my last house, and then every single time before that, when I moved, um, at least when I had a house, because I guess originally when my wife and I were living in apartments, it was a little bit different. But we would always get one of those big, like 20 cubic yard dumpsters, and we would just fill it up with junk that we had no intention of ever using again. Because there's no reason to actually move stuff that you don't plan on using, and yeah, it's been about 7 years, and so my house has definitely got some junk in it. Maybe it's time to do that this summer. But anyway, that's neither here nor there. Like, I'm not sure if the stream is doing okay today. We just don't have very many customers here today, but that's okay. We'll do a little bit of trivia, whatever you guys want to do. Especially if there's only a few of you, you'll all get paid anyway. But we will. Maybe we'll just do some general trivia unless someone has a topic they want to do. But it's been a little while since we've done any trivia, and I know it's kind of fun. But today, I definitely want to murder off these purple ones, all right? And so, because next Monday, we're going to dive into the blues with confidence intervals and hypothesis testing. And the first batch of blues, confidence intervals are, really easy to do. Hypothesis testing, not so much, all right? So we'll definitely spend, how many more? We have three more live streams. Two more live streams before spring break. So we definitely want to get 2 hypothesis testing before spring break. That'll give you something to work on, and then we'll just do these 2 here, regression, way down at the end. I do have videos on everything from this point forward in the class up on the channel there. So, and they're probably going to be a little easier to find by using the search function or just scrolling through the videos on there than it will than diving into these hour-long, live streams here. But just don't let my pace kind of slow you down at this point in time. So if you are on the blues, go check out my go check out videos on all of them. Same thing if you're way down here in regression, ANOVA, chi-square, and non-parametric tests. I got videos on all of these up there. So don't let the pace slow you down. All right, because these 2 they go fast. There's only 6 I think in this, and 6, 7 in this. So this is only 13 topics. If you get all the way through these and you do a couple of these, boom, man, you're probably in A territory depending on how well you've done on the quizzes. And so don't neglect those either. But for today, I'm going to try and plow through as many of these purples as I can. So try and get them all done. And if you have any questions, pop them in the chat there. I'll be happy to cover anything that maybe you're still working on, no matter how far back or how far ahead. So here's light blue. We don't want to do that. Let's switch over to purple here real quick. All right. So we'll get through all the standard normal values today. These are very easy to do once you kind of get the hang of them. But let's just crush each one of these out. Standard normal probabilities. Let's start with this one. I did a little bit of work on this one before. Actually, let's not do this one. Let's do expectation and variance of a random variable. Yes. Okay. So this is one that I was trying to do in a live stream last week, but I didn't have it set up so that we could actually do screen cap. All it was doing was window cap, and so I couldn't show you the Excel spreadsheet in order to do this. But when this one comes up, it does have a rather lengthy explanation. The explanation is not too rough, but this is a lot of math to do. Okay, so the first thing is find the expectation E of x of x. So the expectation of x is just the mean. Okay, it's the weighted mean. So you take this times this, and then this times this, this times this, this times this, add them all up. That's what this means right here. Sum of the probability of whatever your expectation of x is, which this would be the value of x right there. So it sounds really complicated, but that's exactly what they're doing right here. So you can do that, on the Alex calculator here real fast. The other one is a little bit more difficult to do, and that's variance. Find the variance. And so remember that variance is the measure of the spread of our data. So how much does one observation vary from the next? And so we do the same thing in terms of adding them all together, but to get the actual variance itself, you have to take this value right here and subtract it from the mean that you get in this one right here. And so that's this step. So -2 would be this value right here, minus the mean of what we got, which is this right here, square that, and then multiply it by the actual probability, okay? Rinse and repeat for every single one of these right here, okay? Add them all up, and boom, you have your answer. That's your total variance right there. This will never be negative, okay? So that's why you square all of these, okay? So you cannot get a negative answer for this one. All right, this one, yeah, top one expectation, you absolutely get a negative answer for that. But that's a lot of steps, all right? So, yeah, that's a lot of opportunities to jack up the math. And so what I have in here is if you head on over to course modules and go to distributions and confidence intervals, module 3, expectation of variance in a random variable calculator. Just download this, okay, and then open it up, okay, and enable editing. And this is a calculator that will do this problem for you. It's very straightforward. All you have to do is go back to your actual problem. Oh, I don't want to. I don't care about that. Where's my problem? There it is. Way over here. Okay. So you have to punch this data in. So I have 2, 3, 4, and 5. And so we're going to go over here. 2, 3, 4, 4, just 1, 4, and 5. And then these here, just delete them out. If there's extra lines in here, just delete them out. Use your delete key. And then I got to put in the expectation or the probability for each one. So it's 10, 15, 50, and 25. So 10, 15, 50, 25, delete, delete. Okay? Ta-da! There are my answers. All right. So, and all this is doing is the exact math that I just walked you through a minute ago. Here's my expectation right there, which is 3.9. It's the weighted mean of all these. And here's my variance, 0.79. And so if we just put those in, I don't think, yeah, these aren't rounding. Okay. So 3.9. And then the variance right here, 0.79. Check. Ta-da! One more. Same thing, just enter your values, -3, -2, 1, 0, and 1. So -3, -2, -1, 0, and 1. So we have more values on this one, but that's okay. As long as you just delete those out and don't actually change in the formulas, it'll be just fine. So 30, 25, 5, 30, 25, 05. .25 and .15, .25, .15, bam, there we go. So -1.3, 1.3, and variance of x, 2.21, 2.21. This one will always be greater than this one, all right? So that's just because when you add up the variance, you're adding up the variance for each individual observation or possibility, so like this. And just, you know, it's going to be away from the mean. And so the more of those that you add together, the higher that number gets. And so it will overcome your mean fairly quickly. So here we go. Check. All right, now why do we do these? So there's a lot of reasons why we would do something like this. When we actually know the possible outcomes and the probability associated with each, we could figure out, like, okay, what would usually happen? And so that would be the expectation. And then the variance would be like, well, how sure are we about that? Because if the variance is very, very low, then that means it doesn't change very much from one to the next. And so we can be fairly confident in this prediction. So this prediction right here, it's just the weighted mean. So it probably won't be an exact value that's in here, but it'll be close. And so, you know, places where we use this would, like, you know, figuring out the odds of winning a game of blackjack, stuff like that. So here we go. 30, 40, 50, 60, 70, 80. So 30, 40, 50, 60, 70, 80. And our probabilities, these here will always add up to 1. 15.1 and .3.15, .1, .3. And .15, .20, .10, .15, .20, oops, .10. So if we just grab all these, I don't know if you can see this down here, but they sum up to 1. Okay, these will always sum up to 1 because, of course, probability is always 100% that something will occur. So 54.5. Okay. And variance 234.75. 234.75. Check. Done. Easy. All right, so again, use the calculator just because it will keep you straight on the math. All right, so but the concept behind it, very, very simple. All right, let's figure out some more things here. What else? What did we unlock? So we still have a couple binomial problems. Let's go do that one here real quick. I think this one unlocks after we just did the last one. And so remember, binomials outcomes one way or the other. And so this one's actually way easier. You can use the calculator on this one, or you can just actually do the math. I'll show you how to do it both ways. But basically with a binomial problem, it's either or. And so in this case, 94% of workers employed by the university belong to the union. So you're either in the union or you're not in the union. And it wants us to estimate the number of workers in the sample who are union members by giving the mean of the relevant distribution. Okay. And so unlike the last problem, we don't have to weight anything on this one because it's one or the other. All right. And then same thing, quantify the uncertainty of your estimate by giving the standard deviation. And so there's a very easy formula to do this as well. So let's just go ahead and jump in here. I'll show you how to do these real fast. So always do this top one first. All right. So whenever it asks you for the mean, all right, so like this, all you have to do is take whatever value it gives you here. So specifically, researchers reported that 98% of individuals predisposed to allergies find relief. Okay, and then so we have 130 people in the samples. And so this one, who do not find relief. Okay, and so if 98% do find relief, then 2% do not. So 0.02 times the number in the sample, n. So 2.6. Okay, that's your answer for that one. You're always just going to take this, multiply it by the percentage of whatever it's asking for. Notice that this one says does not. This is 98 do, so we just do it by the complement of that, so 2%. And then this one here, okay, so we're going to take the square root of this. So hit your square root key right here. And then we're going to do the exact same thing. We're going to multiply 130. In this case, 130. Wait, man, come on, man. Oh, come on. There we go. 130 times 0.02. Okay. So that's the exact same thing that we did up here. Or you could just take 2.6, but I'm just going to show you the long way to do it here. And then you're going to multiply that again by this value here, the reciprocal or the complement of whatever it is. And so these two pieces here will always add up to 1. Okay, so if it gives you, 25%, it's 25 and 70. If it gives you 40, it's 40 and 60. And then just multiply that like this, take the square root of the whole thing. Boom, that's your standard deviation in this type of binomial problem. It's way easier to calculate than the explanation leads you to believe. So there we go. And so 3 decimal places. So 1.596. There we go. Check. Ta-da! So here we go. Let's do a couple more. All right, number of cards, blah, 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 mean of the relevant distribution. So estimate the number of cards for which she correctly guesses the suit by giving the mean of the relevant distribution. Okay, and so she's guessing the suit. There are 52 cards in the deck, 13 of which are of whatever suit that she would want. And so, but we're going to draw 17, okay? And so it's going to be 17 cards times 0.25. Why 0.25? Well, there's 4 suits in a deck, and she's trying to guess one of them correctly. And so, 1 out of 4 would be her chances. And so on average, she could probably get about 4 of them, not all 17. That would be highly unusual and very suspicious. All right, so same thing. We're just going to take this square root, and then we're going to draw 17 cards. So we're going to multiply 17 times 0.25 times the complement of that, 0.75. Just remember, these two here always have to add up to 1. So there we go. Check. Oops. Oh, no, not check. Enter. There we go. So standard deviation, 1.785. 785. There we go. Check. Ta-da! 2 in a row. Ah, no worries, Matt. Here we go. All right, one more. Same thing, looking for the mean. So, number of visitors in the samples who are actually looking for the company's website. 8% of visitors to the website are looking for other websites. And so after 40-person sample, we're going to take that and multiply it by the number who are actually looking for the website, which would be 92%. Okay, so a complement of 8. So there we go. So of those 40, 36.8 are looking for the website. And then let's quantify the whole thing by multiplying our sample size by, what was it? 0.92 times 0.08. Just remember, these two have to add up to 1. There you go. 1.715. Ta-da! Done. All right, next. Let's see. That should have unlocked 1 or 2 more for me. So, no, okay, so we got to do standard normal values. Here, let's do these in just a second. All right, but let's do some trivia here real quick. Let's just do some general trivia today. Let's see if we can find a new one. Here, shall we? Let's see. Come on, Internet. Cooperate today. There we go. Ooh, here's a new one. It's got all kinds of stuff on it. There we go. All right, how long is an Olympic swimming pool in meters? How many meters long is an Olympic swimming pool? There's a great one. So, how many meters in an Olympic swimming pool? How long is it? So, let's do standard normal values basic. Any takers on this one? Free quiz. So, yeah, good job, Matt. It's 50. It's actually 50 meters, yeah. And so, you know, if you think about it, so what is it? It's 400. It's 8 times up and back. So, yeah, and then if it's 200 meters, then, yeah, it would be 4 times up and back. And so that's why they have, like, the 50-meter sprint, if I'm not mistaken. God, man, I miss the Olympics. Aren't they coming back this year? I don't know. So, I think I saw that Japan is going to hold them again this year. Yeah, yeah, that's not fair. Me too. Yeah, that's okay. But what was it? I think Japan is actually supposed to host them, but I don't think anybody's allowed to come or something. I don't know. So that's okay. All right, so here we go. Let's do standard normal values basic. So when we're talking about standard normal values, there are a couple different ways to do these, but I find that using the Alex calculator is hands down the easiest way to do them. So let's break this down here just a little bit. All right, so P and Z, actually we should do the other one first. Yeah, let's do standard normal probabilities. Let's do this one first, okay? So, and these look a little confusing like this, but this is the first problem, I think, where if you learn to use the Alex calculator, you're going to be a lot better off. So Z, what is Z? Z is, of course, the Z distribution, which is a standard normal distribution. And the standard normal distribution is where we take any values on a given normally distributed data set and we convert them to what we call z-scores. And z-scores are just simply put the number of standard deviations an observation is away from the mean. Okay, so z-scores really handy. All right, so to think about it in some respects, the way that I want you to think about it is like if we took a sample of everybody in the class and measured how tall everybody was, all right, and then took the average of those and say the average came out to be like, I don't know, 5'6" or something like that, and you're 6 foot, okay, but the standard deviation is 4 inches, all right, so, or is 6 inches, right? Yeah, so 6 inches means that you are 6 inches taller than everybody else in the class if you're 6, and then the average person in the class if you were 6 foot, which means your z-score would be 1 standard deviation away from the mean, so your z-score would be 1. Okay, and so it's a really easy way to convert a lot of data to something that's extremely relevant because it'll illustrate immediately whether or not someone's really outside of the norm by just taking their actual height, the variable that you're measuring, and converting that to standard deviations. That's all we do. Okay, and so with this thing right here, what it's asking you to do is do probability lookups. Okay, and so the way that z-distribution works is there's a table where we figured out what's the probability of having a z-score that is this far away from the mean, so like 1.5. 265, just for example. So that's 1.5 standard deviations above the mean if it's positive. What's the probability of finding somebody who's less than that? All right, well, it's going to be pretty high. All right, but normally we do this using a table lookup. I can Google that and show it to you. There she is. Ta-da! So we would look it up on this table. Now you can do it this way, but man, that sucks. So use the Alex calculator because that's what this button. No, I don't want to get off my screen. That's what this button here, right here, does. Is it's just doing a table lookup. All right. And so these problems here are pretty easy. All you have to do is take a look at which one it's asking you, and then line it up with this one right here. See how this is z? So this has the greater sign. So z is greater than something, and notice that this is z is less than something. So whenever you get this one here where it's p to z is greater than, all you have to do is subtract it from 1. So you're just going to take the observation, subtract it from 1 on the other side, which of course will give you the difference, which is everything on the left-hand side right there. And so very, very straightforward. So p to z, negative 1.92, you just punch in this number here directly. Boom, there's your answer. So, yep, 0.973. Right? 3 decimal places. Now think about this. This is a probability. So the probability, if you think about your z distribution, and 0 is your mean, okay, so that's the highest point of your density curve. Negative 1.2 is 2 standard deviations below the mean, okay? So most of the data is going to be bigger than that, all right? It's going to be greater than that, so this 97% should make sense. Okay, this is pretty close to 2, and remember the rule. So 2 standard deviations away from the mean, 95% of our observation is going to be in there. If we're only looking at one side, all right, then it's going to be even bigger than 95%, right? This one here, these ones are really easy. You just punch them in directly. So just hit this key right here and put in whatever it says, 1.89. So whenever it looks exactly the same, see how these match up like this? You can just punch them in directly. So there we go, 0.0229. 0.29. Okay, well, yeah, we're good. All right, and then these ones, it's looking for the probability of z between 2 points, so you're going to have to enter it twice. This is very straightforward. You take this greater one, and you just subtract the lesser one. Okay, so p to z, like this, 2.04, and then click over here, minus, and then just do another one, and this is 0.92. And ta-da, gives you your answer right there. And think about this, all right, so normal distribution, 0 is your mean, p of 0.92, and then 2.04, it's just this little chunk over here, okay? And so it'd be 15. All right, 0.158, check. Ta-da! All right, so I got to do another one here. I did do a couple of these. I think I might have done some of these in class. All right, so, but at the same point in time, just as long as you kind of follow that pattern, you'll be just fine. And use the Alex calculator. It's just way easier. I do have some tools over here that you can use, like this one, this normal probability calculator. It's fine. If you're really jammed up with the Alex calculator, feel free to use this, okay? Right here, because then you can just fill this in betweens and above and below like this, and it works. Okay, but if you get used to using the Alex calculator, then there will be some stuff later when we use the chi-square, the t distribution, the f distribution, that it'll go a lot smoother for you because there's not a website for those. Okay, so but yeah, you can use that website if you so choose. All right. So anyway, here we go, p to z. So notice it's facing the wrong way, so I got to do a 1 minus. Ooh, whoopsie. 1 minus here, p to z, like this. And that's 2.01, enter. So 0.022. Yep. So very small that we'd actually find, very small chance that we'd actually find an observation that was greater than 2 standard deviations above the mean, which is what that's telling you. Okay, so 2% sounds about right. This one here, we can just punch it in directly. So negative 1.94. So the probability of finding a z-score that is less than 1.94, so this is 2 standard deviations below the mean, almost. And so this one's going to be tiny as well. So there we go. So 0.026. If you ever get a negative value in these, you did it wrong. Okay, so redo it. All right. All right, here we go. This one right here, all we have to do is subtract the larger one, 1.68. Or subtract the smaller one from the larger one. There we go. That's the correct verbiage right there. 0.41. Oh, 0.41. Like that. Yep. Bam. There we go. 0.29. 4. Check. Easy breezy. All right, we're just crushing out some purples today. So let's let's make sure we get them all. So there we go. We just unlocked a few more. That's right. We do have F distribution in here, but we have to do our normal distribution. So let's do those. So the next one that you probably want to do are these standard normal values basic and standard normal values advanced. So here we go. Let's do this. All right. So now it introduces a new concept. All right. So we have. There we go. Man, I don't know what's going on with the internet today, guys. Sorry about that. Getting funky messages here. But hopefully this is working. But anyway, let's do this. Because it was working just a few minutes ago. So hopefully we're all back up live. But anyway, where was I? Yes, and so this one you're going to actually use the probability here to calculate what would be the cutoff value or the specific z-score that would give us this probability. So it's just like the last problem we did, it's just doing it backwards, all right? And instead of using this button to figure that out because we don't have a value, we have the probability, we can use this z-box button right here to do the table lookup. And so for example, this one right here, p to z, and notice that these line up like this, is 0.6950. And so to figure this problem out, I hit the Z-box button here. And notice that I don't put the 0.6950, okay, in here. And that's because this table lookup is from left to right, and this one is from right to left, okay? That's just the way they wrote them, okay? And so this one's actually backwards. So when you have one where, and the thing that I try and tell my students on this one, this is cheesy as heck, but it will help you. When the alligator eats the C, eats the Charlie on this one, subtract from 1. Alligator eats the Z, just punch it in. Okay, so that'll make some more sense here in just a minute. But let's go ahead and get started here. All right, so see like this one right here, alligator eats the Z, okay, and so you can just punch it in directly. 0.7764, like that, okay? And so our Z-score, this one you can get a -1, 0.76. 2 decimal places, check. Okay, ta-da. All right, let's get the other type in here. So, okay, this is the third type of problem that you see, and a lot of people get freaked out by these, but these are actually the easiest ones to do, where you have C's on either side, because it's a normal distribution. You're looking for cutoff value on either end, so this is really straightforward. What we do is we take 1, we subtract our probability, so .9281, okay, chop that in half. So take that, whatever you get, divided by 2. Yeah, absolutely. I'll be getting to that one in just a sec. So take that and divide it by 2. I think I just did that. Yes, I did. So take that, divide it by 2, hit enter, and just punch it in now. Right like that. There's your answer. So it's going to be positive 1.79 and negative 1.79 on either side. 2 decimal places. So this is going to be 1.80. Check. Ta-da! Next. Here we go. Alligator eats the Charlie. Alligator eats the Charlie, subtract from 1. So 1.1 minus .2981. So just subtracting the probability. And there we go. Now we're going to punch that in here. Hit enter. And there's our answer right there. Negative 0.52530. 530. There we go. Check. All right, takes a little bit of practice, but the more of those you do, the better off you'll be. Okay, so oftentimes when people get these wrong, they either forget to, punch in the negative, if it is actually a negative z-score, or they're just looking at it on the wrong side. So remember, alligator eats the Charlie, subtract from 1. Alligator eats the Z, just punch it in directly. If it's got Charlies on either side, take 1 minus the probability, chop it in half, punch that in like that. There you go. So I do have a video up on that one. That one is very, very frequently requested. Next one is going to be advanced values. This one is a little tricky. There's one problem on here I consistently jack up, and I think it's this one here. Okay. Yeah, whenever you have the C on the left-hand side, you have to add these together, if I'm not mistaken. So, yeah, you have to add these together. If you get this one and the Charlie's on the right-hand side, I'm pretty sure that's the one that you have to subtract. And that's the only thing you have to remember with this, because you'll be getting one or the other, if I'm not mistaken. Let's dive in here. It's been a while since I've done this one. Yeah, so see, this one's got the Charlie way over here on the right-hand side. And so on this one, what we're going to do is we are going to take this value and punch in this value into here, right? Hang on. No. Oh, man, now I'm confused. I always have to look this one up again. All right, so in this one, area into the density curve, we can view the value. Yeah, so that's right. So we're going to do it this way first, where we'll take this and then subtract the probability of that, and then we punch in the remainder to get this. And so, yeah. And these ones are Charlie on the right-hand side. These are the ones where you subtract. Okay. All right. So let's do this one again here. Let's try it again. All right. So this one's on the left-hand side, so we have to add on these. So when it's on the left-hand side, you add these together. And so we'll start with this first. P to Z, negative 1.19, like that. And then add 0.0811. There we go. Punch that in to this one right here, and there we go. 0.848 should be right. Nope. What am I doing wrong? You do add these together, if I'm not mistaken. Proceed. Yes. Yeah, so we add these together. Probability Z. So we have to subtract it from 1. Yeah, I always get screwed up on these. Let's try it again here real quick. So it gives us like this. And so we want to do probability of Z negative 1.19. Isn't that what I got last time? So it's going to be 1 minus that. Yep. 8830. Okay. All right. Man, that's an extra step in there. There's got to be an easier way to do these. So, no. So, yeah, it's on that side. Man, that's confusing. So, yeah, if it's on the left-hand side, 1 minus whatever this is, add that, then punch that in directly. Oof, man, that's a lot of steps to try and remember. Let's try it again. Here we go. We got the exact same one here. Okay, and so, oh, no, actually, this is the other side. So, it's P to Z, .64. Enter that, subtract .2404. That's our Z right there. Punch that in. 0.003. That doesn't seem right. 0.004. Check. Now. Oh, man. Oh, subtract. Yeah, you got to subtract these. Okay. All right, so let's get this sorted out. So C is on the right on this one. We have to take 1 minus P to Z to 604. So you have to do that in either step. So it's always 1 minus. And then in this one, it is whatever you get, subtract the .24. Okay? And then the other one, this one's add. So let's check out the explanation on this one. So yes, C is on the left. You always take 1 minus whatever it gives you right there. Take that, add it to that, and then punch it in. Okay. Here we go. C is on the right. So we have to subtract. So it's always 1 minus P to Z of whatever it gives you, the Z score. There we go. And then subtract .1238, whatever's left. And punch that in. There we go. 1.880, right? Check. There we go. Got it. All right. It only took me like 10 minutes. All right. C is on the left here, so we're going to have to add. And so always take this, subtract 1 from 1 minus. There we go. Enter. So since C is on the right, we add these two together. So .55 or nope. .0 nope. 0.6871. There we go. Okay. Punch that into Z. There we go. negative 2.019. So yeah, that makes sense. So negative 2z would be very low z. So yeah, quite a bit of 68% of the values would actually fit between that and 0.55. All right, that sounds about right. Cool. All right, finally got them. Let's do one more. So this is c again on the right. So we're going to add, or no, we're going to subtract on this one. So it's 1 minus p to z of negative 1.125, right? Nope, negative 1.25. Bam. Take that, subtract this, 0.8711. This can be very small. Punch that in. There we go. 1.991. Yeah, so most of the observations, 87% would fit between negative 1.25 and 1.991. Okay, cool. There we go. All right, folks, hope I didn't hurt you. I hope I didn't screw you up on that one too bad. Just remember, there's only two types of problems here. C's either on the right or it's on the left. Regardless of which side it is, always start these problems by taking your Z or your Alex calculator here. Take 1 minus P to Z, punch in whatever number it gives you, negative 1.25. And remember, if it's C is on the right, you're going to subtract that from this or this from that. And if C is on the left over here, then you're going to add these two numbers together. Okay, so that is the trick to doing these. Man, I should have practiced that one before we did it on the live stream, but I always do that every single semester. All right, normal versus standard normal density curves. Let's go do it. I think I did this one in class the other day. Oh man, there's no way we're going to get to all these today. Shoot. So we might be getting just a skosh behind here, but let's go do that one for you, and then I'll crush out a couple more of these. No, not that. I'll crush out a couple more of these for you. This one right here, normal versus standard normal density curves. This one is way easy once you get the hang of it. And so you need to do this one before you do any of those other Z ones, because this is where it really explains to you how the standard normal density curve works. Why are we even using the standard normal density curve? Well, it takes data regardless of where it came from, and as long as it's normally distributed, we can crush that down to a standard normal density curve. It's basically like zooming out. All right, and then we can do a lot more in-depth analysis on it. And so you have to take something that is observational data, so I mean this is what we actually record in a while, and translate it into this. This is the standard normal density curve, this pointy thing right here, okay? These are z-scores down here, where these are actual values. Same thing with this. So as opposed to these are actual standardized. These are standardized on this one. And so it's just asking you to translate this into that. And so to do so, you're going to use the Z formula. Z formula is very straightforward. Z always equals X, whatever your value of X is, minus the mean, okay, all over your standard deviation. So X minus mean divided by standard deviation. Boom. That'll always translate to a Z-score for you. And so if you get a problem like this, all right, so notice that we have these two values right here. We have to punch both of those into the Z formula. All right, and so this one right here, negative 7, start with that. Negative 7 minus my mean. My mean is given to me in the problem right here, where you can look at it. It's right here too. So negative 3. Do this in parentheses so you don't jack up the order of operations on this one. Enter. Negative 4 divided by your standard deviation, which is given to you in the problem right here. Also 4. Okay, it's negative 1. Okay, and so negative 1, this is the z-score for this observation. So negative 7 has a z-score of negative 1. It is 1 standard deviation away from the mean. And so we take our line here, and we go down here, negative 1. So just draw a line right there, and there you go. See how those match up? Right, like that. And let's just do it for the other side. So this one's negative 1 minus our mean. Oops. Minus our mean, which was negative 3, minus negative 3. Enter. 2 divided by a standard deviation, 4. So this one is 0.5. So it is half a standard deviation above the mean. This value of negative 1 here is 1/2 a standard deviation above the mean. And so we just go down here to 0.5. So it'd match up right like that. Click my shader, get everything in the middle. They should look roughly the same. Yes, I get this with much taller data, but that is the point behind the standard normal density curve. Okay. And so we're taking our normal values and then actually putting it on standard normal. They'll always look roughly the same. Okay, Check. There we go. Let's do one more. Easy breezy. So look at this one. This one's going to be way down here. So it's going to be like something down here, shade all the way over. Now, eventually you do enough of these, you can kind of do them in your head. Okay, and let me show you how to do that here real quick. My mean is 4. My standard deviation is 2. And so this observation of 0 here is 1 standard deviation, so 1, 2, that's 1 standard deviation. 1, 2, that's another standard deviation. Okay, so it is -2. Okay, so it's going to be -2 standard deviations because there is, my standard deviation is 2. That's 1, 2, 3, 4, which could be 2 standard deviations. 4 divided by 2, 2 standard deviations right there. And so, ta-da, I can just do it right like that. Check. Okay? Don't feel bad if you can't do them in your head like that. It's totally fine, all right? So, but after a little while, you do get a little bit. What if it says greater than 0? What do you mean? On which one? Greater than 0. I don't think on this one you have any ones where it says more than or less than. Not quite sure which one you're talking about there. Yeah, if you could clarify, that would be awesome. But hopefully this one helps, okay? Hopefully this one helps right here because, oh, I see what you're saying. This is the shaded region of probability of obtaining a value from the distribution that is greater than 0. Well, yeah, so this is 0 right here. That's just an observation. And so it's asking you, what about greater than 0? So it'd be everything to the right of 0. If that's what the problem is asking you, okay? I don't even pay attention to that. To tell you the truth, I just looked at this thing right here. Where is it? Okay, it's at 0. And so how many standard deviations away from the mean is that? Here, let's do one more just for funsies. So here's -7, and my mean is 1, and my standard deviation is 4. Okay, so this one, I don't want to do this one in my head because that doesn't divide evenly. Well, actually it does. It's 8. So there's 8 between here. So 1, 2, 3, 4, 5, 6, 7, 8. 8 divides by 4 twice, and so it's 2. And so it's -2 standard deviations away from the mean, right like that. But it's looking for everything that is less than -7, which means less than, left than. Bam, that one right there. See, I could do that one in my head too. If you can't do it in your head, it's absolutely fine. But the principle is really straightforward, okay, once you get the hang of it. If not, just punch in the Z formula. Z equals X minus mu all over standard deviation. Whatever value it gives you here, where the line is, that's your value of X. All right? Cool stuff. Hope that helps. Let me know if you have any other questions on that. But we got to go back in here and do a couple more of these problems because we actually, with missing class 2 weeks ago, was actually kind of put us in a little bit of a hole. But that's okay. We will get through these. Let's do, what time is it? 3:18? Yeah, let's go for about 10 more minutes. We will ignore these 4. T distribution, central limit theorem. F distribution, chi-square. Central limit theorem, this one's really easy, okay? If you're stuck on that one, go over here. Central limit theorem for sample means calculator. Use the calculator. Okay, so, and then, but these ones here, normal distribution, finding probability, and then finding a raw score. These are ones that people get jammed up on all the time, so let's do this. Here, real quick. Oh, is that the one that I'm on? Yes, okay. So this one, you have to use the stuff that it gives you, punch it through the Z formula, and then use the probability key on the calculator right here, all right, to figure this one out. And sometimes it's 1 minus, and sometimes you can punch it in directly. So, but it's basically word problem versions of the ones that we did a little bit before, okay? And so, for example, according to a recent survey, the salaries of assistant professors have a mean of 4,756, standard deviation of 7,500. Assuming that the salaries of assistant professors follow a normal distribution, find the proportion of assistant professors who learn at least $45,000 a year. And so, in this one, what we're going to do is we're going to take that $45,000 a year, we're going to subtract the mean, then we're going to divide the standard deviation. That will give us a Z-score, okay? That Z-score is something that we can punch in the calculator depending on whether we're looking for greater than or less than. If it's less than, you subtract from 1. If it's greater than, you don't, okay? And so here we go. Let's try another one here real quick. All right. Certain test is designed to measure the satisfaction of an individual with his or her relationship. Oh, yeah, I bet you this is accurate. Suppose that the scores on the test are approximately normally distributed with a mean of 55 and a standard deviation 9. An individual with a score of 40 or less is considered dissatisfied with the relationship. According to this criteria, what proportion of the people in the relationship are dissatisfied? And so we're going to take our X value, which is 40, okay? And then subtract our mean, which is 55. Enter. Divide that by our standard deviation, which is 9. Okay, so we get this right here. It's looking for everything that's less than that. So we're going to punch that into the Z calculator, but we're going to take 1 minus. All right, so it's looking everything to the left of that. So there we go. What proportion of people in relationships are dissatisfied? So 95%. I don't think this is right. Maybe you don't subtract this. Normally distributed with a mean of 55, standard deviation of 5. Was the last one greater than or less than? I always get these backwards. So, mean of 55, standard deviation of 9. According to what proportion, so yeah, 55 is the average. There's no way that this one's correct. And so let's undo that, and then let's just do it directly like that. See, that seems about right. Because this is pretty far. That's at least a standard deviation and a half away. Yeah. So 55, 9, so it's 15 difference. Yeah, I bet you this is right. 0.04748. 478. There we go. Check. Yep, okay. All right, so yes, less left then you punch it in directly, more than it's 1 minus. There we go. All right, suppose the annual rate of return for a common biotech stock is normally distributed mean of 5% and a standard deviation of 5%. Find the probability that 1 year's return of the stock will be negative. Okay, and so this one's a little tricky because it says what would it actually be in order for it to be negative? So it'd be anything less than 0. Does that make sense? Okay, and so our X value, and this one's actually 0. We're going to subtract 5%. 0. Actually, I think we can just do it like this. 5%, and then divided by 5 gives us a z-score of negative 1. Okay, punch that in the calculator here like this, and it's looking for everything less than that, so we can just do this directly. And so 0.1581587, right? Check. Yes. So don't let the verbiage on these. It says less than 0. If it's negative, it's less than 0. Okay. And so your X value would be 0. Subtract 5. You don't even need to decimalize these just because it's on a standard normal curve. That might be a little bit advanced, so you can always do it as a decimal. Just understand that if you did that one, you'd have to enter 0 as a decimal. Otherwise, you'd come out to what? 0.95? Yeah. So maybe just do those straight up as integers. So anyway, suppose the time required to complete 1040R tax reform is normally distributed, mean of 100 minutes and a standard deviation of 15. What proportion of 1040R tax forms will be completed at least 103 minutes? So 103 minus our mean, which is 100, divided by our standard deviation, which is 15. So at least would be, I have to think about this. If it's at least, then it is anything equal to or greater than, right? Yes, equal to or greater than. And so this one, we do want to do the 1 minus. There we go. Yep. 7. Yep. 103.15. Yeah, that looks right. There we go. And you might be asking yourself, well, how can you tell whether or not it looks right? Well, it's just based upon understanding the normal standard density curve. Okay, so if it's 1 standard deviation, and if it's anywhere between those two, 1 standard deviation greater or 1 standard deviation less than the mean, that's 67% of your observations, 68% of your observations, and then 95, and then 99. And so once you learn how to kind of navigate it a little bit, you can kind of eyeball things and say, no, that's not right. Don't worry if you don't get there. It's absolutely fine. So anyway, let's do one more here today. And then, oh man, I've been jacking you guys out of trivia. Let's do some more trivia. Sorry, totally forgot. Let's see. Oh, here's a good one. Who actually named the Pacific Ocean? Who named the Pacific Ocean? I'm sure it had a name before the Pacific Ocean was called the Pacific Ocean, but who decided to call it the Pacific Ocean? There you go. There's a history question for you. So those are always fun. Oh, man, I got going on math here too much. Trying to get caught up. Man, my allergies are killing me. So who named the Pacific Ocean? Coincidentally, also the first individual. No, it wasn't Lewis and Clark. That is a great guess. Okay, but it was actually named before that by the guy who actually sailed it. And, well, he tried to sell it, but was murdered in the Philippines. They named a very famous what is it, GPS device after him. I'm giving you all the hints now, man. There you go. Good job, Guts. You got it. It's Magellan. You got your free quiz today. So I had to deduct half a quiz out of that just because I'm giving you all the hints. So that's okay. All right, here we go. Let's do a couple more of these. Finding a raw score, normal distribution. This is one that freaks people out because the explanation on this problem sucks. All right, I'm going to show you the fast way to do this. All right. So basically with this one, all you're going to do is reverse engineer the formula, okay, because it's going to give you the probability, the z-score. It's going to give you the, well, I think it gives you the probability. Yeah, it gives you the probability. So you have to look up the probability using this right here, okay? And then that, of course, gives you the z-score using the z-box, all right? So, and then you use that to look up the z-score. Then you multiply it by the standard deviation, and then you add the mean in order to get your value of x. Okay, so it's just reverse engineering this entire thing, just a little bit of algebra. If you did really well in algebra, you probably look at this problem and be like, oh, I got it. But if algebra wasn't so much fun for you, then this explanation here is absolutely torturous because it's trying to encourage you to actually do all of that here in this button, and it's just a pain. Okay, so it's much easier to do this the other way around. So here we go. Let's do this one. Distribution of scores on a standardized aptitude test is approximately normal with a mean of 520 and a standard deviation of 105. What's the minimum score needed to be in the top 20%? So we're looking at 80% and above. Okay, so carry your intermediate computations to at least 4 decimal places, blah, blah, blah. We don't care about that. And so the way that we do this, we're going to use the z-box, and we're going to look for everything that's .8 and above. And so there's our z-score right there. So 80%, maybe that's backwards. So let's see. Mean of 520, standard deviation of 5. What is this mean score? It's be in the top 20%. Yeah, so this is backwards. And so it's actually z.20, right-hand side. Look up. There we go. .84. Negative 84 would give us a lot more values. Positive 84 is just a few on the top. And so that looks right there. So we're just going to take that and multiply it by our standard deviation, which is 105, and then add our mean, which is 520. Boom, there's our answer right there, 608. So you'd have to have at least 608, nearest integer 608, in order to get in the top 20% on this test. This should make sense. If the average is 520, 608 is a pretty good score, and so top 20% would definitely be higher than whatever the average is. So there we go, check. Ta-da! Next, next. Here we go. Look at this. Calcium levels in people are normally distributed with a mean of .93 and a standard deviation of .4. Individuals with calcium level, bottom 5% of the population are considered to have low calcium levels. Find the calcium level that is the borderline between low calcium and those not considered. So bottom 5% is just the very tip on the way left-hand side. And so this one's going to be z.95. So the complement of that. And so there we go. Yeah, so negative 1.644 is a very low z-score. And so this one's going to be really low. And so we take that, multiply it by our standard deviation, which is .4, and then add our mean, which is 9.3. And there we go. That's our answer. So it'd be 8.64. 1 decimal place, 8.6. Cool. Check. All right, piece of cake. One more. Here we go. Risk-taking is an important part of investing. Really? You think so, Dave Ramsey? Sorry, I'm getting a little snarky there. So anyway, in order to make suitable investment decisions on behalf of their customers, portfolio managers give a questionnaire to new customers to measure their desire to take financial risks. This is actually true. You do take a risk assessment. So the scores of the questionnaire are approximately normally distributed with a mean of 49, standard deviation of 15. Customers who score in the bottom 5% are considered risk adverse. What is the questionnaire score that separates customers who are considered risk adverse? So the bottom 5%, so we're looking for the cutoff score. So reading it from left to right, top 95. And so there we go. Very low z-score right there, negative 1.64. Take that, multiply it by our standard deviation, which is 15, and then add our mean, 49. And so people who score 24.3 or less are extremely risk adverse in this one. There you go. All right. Cool beans. 68. We only got a couple left in here. Let's see if there's one more in here just to kind of get us in a good spot. So T distribution, F, and chi-square. So T, F distribution, and chi-square, you can put these off for a little bit, okay? Because you won't see T again until you get to the hypothesis testing, and then I think there's some confidence interval questions that deal with that. Same thing with F and chi-square. These two here in particular are unlocking things that are way down the road, okay? And so if you get to this one, you're freaked out by it, don't worry about it too much. But definitely go check out my YouTube video because both of these are very, very straightforward to do. The one that you should do is the central limit theorem. So this is actually all that you'll see on Chapter 8. And so it's very straightforward. We'll be sure to cover that in class on Wednesday. And then I'll do another quick video of it on Monday as well. And so we will finish up on Monday so that we can actually move on to confidence intervals and hypothesis testing. And noticing right off the bat, I'm already getting some of these. If you're starting to see some of these in here, determining null and alternative hypotheses this weekend or so, definitely go in and check out the YouTube videos because I have videos on every last one of these. And I don't think any of them are more than 10 minutes long. And so, but with that being said, we will definitely have to dive headfirst into all of this stuff next week because I do want to get to hypothesis testing before we go on spring break. Okay? So, and that's kind of the end game for the class. Now, yes, I understand after hypothesis testing, there are a couple other chapters in there, which we probably won't cover until the last 2 weeks of class, but also understand that once you get through hypothesis testing, the class is basically done. Okay, so that's the last thing I really need you to pull from the class. All right, so we will definitely we'll dive into that head first next week, and make sure that we get at least started on that before spring break rolls around. All right, okay, so that's enough math for one day. Man, we covered a lot, so I think we got about seven topics done today. And so if you're jammed up on anything the next couple of days, definitely come see me or ping me. Yeah, I guess you can't come see me. But on Wednesday, we'll do the Zoom session again. And if you are getting a little bit behind on this stuff, it is time to start plugging back into that and being there for it. But if you feel comfortable with it, and if you're doing pretty close to where I am on my pie here, so if you're pushing up around 70, you're in great shape. All right, so push. If you're not there yet, yeah, you got some work to do this weekend. So please, use all the resources that you have available. I'm here. My YouTube channel is up all 24/7, and likewise, I am available on Wednesdays for one-on-one time if you need it there as well. Okay, all right. So let's see. One last trivia question for the day. Let's see if we can find an interesting one. Oh, these are history questions. Let's do something. Ooh, what is the rarest M&M color? I didn't know this. In a standard bag of M&Ms, which one is the most rare? Here's a stats question for you. Rarest color of M&Ms in a normal bag. Which one is it? So go for a free quiz. I'm curious as to what the actual probability is now on this one. So, my understanding is that every bag of M&Ms is basically standardized, meaning that, the chances of you actually getting a bag full of green M&Ms is like virtually zero, just because of how well they're mixed. Tan, yeah, well, actually, I don't know. I don't know if they even make the tan ones anymore. But the answer is brown. All right, so I'll take tan. All right, so that's fine. No, it's not blue or green. It's actually brown. And I remember reading a study on this a couple of years. Well, I don't even know if it was a study or if it was just a blurb in a stats book, where the tan M&Ms are gone. Because they did like this long this thing where if you put M&Ms out and you separate all the colors, which are the ones that people grab for, and so like the blue ones and the green ones are like some of the ones that are like the most popular, and the tan one was like the least popular. And so I think it was like a long time ago when they introduced the blue ones. Then there were days where there were no blue M&Ms, if you remember those. Where they basically kept blue and got rid of tan, if I'm not mistaken. I'm not sure though. So let's use the Google on this one. Is the most rare color of M&M. Tan. Oh, okay. So this one says tan. Well, I'll give it to you, but it's actually it's brown. Red was replaced in orange. Yeah. Nah. Let's see what Yahoo has to say on here. Yeah, see, there's no tan ones anymore. But there were tan ones at one point in time. I can't remember. Anyway, whatever. What was it? There's another cool M&M story that it ties to CSU Pueblo directly. Who was it? Back in the 1980s, when it was actually called USC, I think it was Van Halen played at USC in the basketball arena, and they caused like $20,000 or $30,000 worth of damage to the basketball floor because David Lee Roth had this thing where he wanted to make sure that venues were paying attention. And so one of the ways that he made sure that venues paying attention was he asked for a bowl full of nothing but green M&Ms. That's one of the classic like Rolling Stone, kind of stories. And so they brought him a bowl of M&Ms, but it had more than just green ones in it. And so the guy went and completely ape and actually trashed part of CSU Pueblo. So, true story. Look it up someday. But anyway, that's a good note to end on. We'll call it quits here today. So thanks for being with me here today. We'll catch you all on Wednesday. If you have any questions, I'll stick around for just another minute or two, and we will try and get you taken care of. But on that, you're off the hook. Have a wonderful afternoon. Enjoy the weather while it lasts. I hear it's supposed to be a little bit crappy tomorrow, but we're getting to that point in time of year where weather, when it gets crappy, it doesn't stay crappy very long. So hopefully you enjoy it. All right, folks, that's all I got for you. Take care now. Bye. You bet, Morgan. Oh, jeez. Bye, Harley. Good job today. At least I think that was Van Halen. Oh, man. Now I have to look it up. Wiki. I know it's on our wiki. I know it's on our wiki. Popular culture, urban legend. $85,000 damage to the Masari Arena. Oh, I'm sorry. It was brown M&Ms. I didn't mean to talk smack about green M&Ms. So there you go. Actual story as told by David Lee Roth in his autobiography. He admitted doing about $12,000 backstage damage after noticing brown M&Ms. You bet. Yeah, no worries, Mandy. I'm glad it helps. All right, guys. I'm out of here, so we will catch you all on Wednesday. Take care now. Bye.